In this third section, we're going to look at the polarity and how that goes along with your molecular shape in the VSEPR. Okay, bond polarity is a measure of how equally the bonds are shared. And we're talking about when they are shared, we're dealing with the electrons. If the electronegativity difference is large, the bond polarity is large. So in a particular bond, if we now take the shape into consideration, you can have a molecule that has polar bonds, but the molecule overall is nonpolar. And then look at what's called an overall dipole moment. That's the sum of the dipoles, meaning there's a sum of the polarities. Dipole is just a fancy word for polarities. Dipoles, two poles, a positive side and a negative side. They talk about an overall dipole moment or a dipole moment and wants to know about where's your partial negative, where's your partial positive. Remember, bonds are polar, meaning that one end is partially negative, one end is partially positive. Where an ionic bond is fully negative and fully positive. Okay, so let's look at some examples. Okay, so we've got carbon dioxide here in the upper left where its overall dipole moment is 0, meaning it is a nonpolar molecule, because even though this carbon-oxygen bond is polar, the O is closer to fluorine. O is more electronegative than C, so the electrons want to stay towards oxygen. This is how we write that. You put a little plus sign with an arrowhead. This means that this is the negative side and this is the positive side. You will also sometimes see a symbol that looks like a little S. It's a delta and a little positive. That means that it's partially positive and partially negative. But notice here how this one is pointing to the right, this one is pointing to the left. So in essence, you are canceling one another out. If we look at water here on the right, okay, hydrogen is going to be the positive end, oxygen is going to be the negative end because oxygen is closer to fluorine. So they go towards oxygen, but these do not readily cancel. The reason they don't readily cancel, even though that O is connected to two things, is because even though you don't see it here, O has two lone pairs. So O actually has 4 things around it, which means this bond angle here is not 180 degrees. This bond angle is actually 104.5. Here, the bond angle was 180, so they were directly across from one another. Here, they are not directly across from one another, so these do not cancel. So what you end up with is an overall dipole moment in the direction of the oxygen, meaning overall, this thing will have its electrons towards oxygen and not towards the hydrogen end. So we see that here in the other examples. We've got a polar CH bond with the chlorine being more electronegative, so the arrowhead goes towards chlorine. We've got a nonpolar molecule with the fluorines because they all pull equally away. Because here we have 120 degrees, so they're all equal. This one is polar because even though carbon has 4 things around it, one of them is a chlorine, so this pulls differently than the H's. The electrons really want to sit around chlorine. Whereas here they're all chlorines, so they all 4 cancel. Even though they're not 90 degrees, these angles are all equal at 109.5, so they all pull equally on the electrons, which means they all cancel out. But as soon as you have this trigonal pyramidal with a lone pair on top, now nothing can cancel out a lone pair but another lone pair. In order to have lone pairs that cancel out, just like atoms that can cancel out, your lone pairs have to be 180 degrees apart, just like your atoms have to be 180 degrees apart. So just because you have 2 lone pairs, like you do up here in oxygen, these 2 lone pairs do not cancel out as they are about 104 degrees apart or so. You have to be exactly 180 degrees like these oxygen atoms are in this carbon dioxide bond.